this section of 6.7, we're going to look at inverse hyperbolic functions. So reading it, it's hyperbolic, inverse hyperbolic sine, inverse hyperbolic cosine, inverse hyperbolic tangent. So remember with inverses, basically just the x and y are switching places, right? So if my y, it's y equals inverse hyperbolic sine of x, the angle, then the inverse would be switching the x and y's. And the inverse of the inverse is just the regular. So the inverse of hyperbolic, the inverse of the inverse of hyperbolic sine is just hyperbolic sine. So the x and y switch place. So I don't know if that made sense, but the inverse of the inverse is the regular. Basically, that's what that means. Okay, and then here are the graphs. So the inverse on hyperbolic sine is, our domain is all real numbers and our range is all real numbers. Cosine, we have to limit our domain from 1 to infinity. And so then our range is going to be from 0 to infinity. And then tangent also has a limited domain from -1 to 1, but its range is all real numbers. So that's what their kind of graphs look like. Just like when we had to limit sine, regular sine, cosine, and tangent, we had to limit those, so then their inverses would be functions. So the same kind of idea here of limiting those domains. All right, so now let's go ahead and take a look at kind of what they actually equal. So this is what they actually equal. So inverse hyperbolic sine actually equals ln of this, okay? Inverse hyperbolic cosine of an angle actually equals ln of the number, okay? And inverse hyperbolic tangent equals 1/2 times ln of this, okay? So that means when I'm taking inverse hyperbolic tangent of say 2, okay? Actually, I can't do 2, right? It has to be in between 1, so let's do 1/2. 1/2, I would plug a 1/2 in here and in here, okay? And you can see now why this can't be greater than 1, because if I had something greater than 1 at the bottom here, it would be negative, right? And then this whole thing would be negative. And then you can't take the ln of a negative number, so that's why it has to be bigger than 1 or something like that. All right. So let's go ahead and prove this first one. So let's go ahead and prove it. So we'll go ahead and prove this. Let's see here. So in order to prove it, we'll first just go ahead and let y equal this. Inverse hyperbolic, that should be an h there, hyperbolic, inverse hyperbolic sine. So let y equal that, so we'll take the inverse of that. So the inverse of the inverse is just the regular, right? So that'd be just hyperbolic sine. Switch the x's and y. Okay, and now we can just go ahead and actually write what this is. So I think it's on page like 464, 462. Hyperbolic sine is e to the x minus e to the negative x all over 2. Right, that's what hyperbolic sine actually equals of an angle. And I guess it wouldn't be x, it would be y, because I have a y right here. All right, and that equals x. And then I can just go ahead and simplify this, multiply both sides by 2, you know. That would cancel, move that over. So e to the y minus 2x, set it equal to 0, minus e to the y equals 0, set it equal to 0. Then we can go ahead and rewrite. Multiply everything by e to the y. So multiply by e to the y, so that'd be e to the y plus y is 2y. So as long as I do it to both sides, that's fine. This is what's nice about this is a negative y and a positive y is going to cancel out to 1. E raised to 0 is just 1. When I multiply 0 on this side, just 0. So now I have a quadratic looking form, right? I could let u equal something. U equals e to the y. So then this would just be u squared minus 2x u minus 1 equals 0. So it kind of looks like a quadratic. My a is 1, my b is right here, and here's my c. So then I could do quadratic formula and go ahead and solve this for u, or solve for ey. Because I have my b, opposite of b would be a 2x, plus or minus the square root of b squared. So that would just be 4x squared. And 4 times a is, or negative 4 times a is negative 4. Negative 4 times negative 1 is a positive 4. So I just get that all over 2a, so all over 2. So then you can go ahead and factor out of this one. You could factor out of 2. So there'd be a 2 out of, or actually a 4, sorry, factor out of 4. And now since I have multiplication here, now I can simplify that. Square root of 4 is 2. So I just have this. Then I can factor out everything with the 2. So I get that. And then again, the negative's not going to matter if this is greater than 0. So, I mean, anything I plug in here is always going to be greater than, right? Because whatever x is, this is just going to be a little bit bigger, because this plus 1 is going to be a little bit bigger than x. So when I minus that from x, it's just going to be a negative. So really that negative there is going to be irrelevant, because I can't even take the ln of a negative anyways. So when I take the ln of both sides to bring down that y, that negative doesn't really matter, because I can't take the ln of a negative. All right, so there's my answer, and I know what y is. Y is inverse hyperbolic sine of x, right? So we can see that we proved it. Okay, let's go ahead and take the derivative of inverse hyperbolic sine. We're going to prove that it actually equals this. So again, we'll go ahead and let y equal inverse hyperbolic sine of x. So that means I take the inverse of that. I just get hyperbolic sine, but I switched my x and y's. And now I can use the definition of it, or actually not that route. Let's do this. Let's just take the derivative of both sides. But because I'm taking the derivative of this with a y in terms of x, that means I'm going to have to do chain rule, right? So I take the derivative of hyperbolic sine, which is hyperbolic cosine, leave y the same, and then take the derivative of the inside, y prime. And this is just going to be 1. Okay, now I can just solve for y prime, because that's what I'm looking for, right? The derivative of this, which is this, and derivative of that, same thing. Invert 1 over hyperbolic cosine of y. So then I can switch that back to secant, hyperbolic secant y equals y prime. No, don't want to do that yet. Let's go leave it here. But I do know that this is true. This is squared minus this squared. That equals 1. So that top would equal, or let's solve that. Leave that one there. And if we solve this, we can just add hyperbolic squared of sine. And so the squared equal 1 plus that squared goes outside the h. Okay, and then to get rid of the squared, we can square root both sides. So I have 1 over hyperbolic cosine of y. Well, hyperbolic cosine of y is the square root of 1 plus hyperbolic sine squared of y, which hyperbolic sine squared of y is just x squared. So this is just 1 over the derivative is 1 over the square root of 1 plus x squared, which we can see that's what it equals. So there you go. That's how you prove the derivative. The rest of the derivatives are on page 466, and those are the ones that you're going to do in the first part of your assignment, is use those derivatives to find out. And you're going to have to do chain rule a lot, chain rule and product rule. And then on the next video, I'll show you how to do the integrals and the derivatives. I'll do some examples of those. So here's an example of the derivative. So I'm taking the derivative of a inverse hyperbolic tangent of this. So I'm going to do chain rule, right? So remember, chain rule is the derivative outside, which that is secant. So page 4, what did I just say? 466, yeah. 466, so that's 1 over 1 minus x squared. Well, my x squared is, actually that is being squared. Okay, and then I times that by the derivative inside, or just u prime. I guess I could have just used u prime. It's cosine of x. So this is cosine of x over 1 minus sine squared of x, which is just cosine x over cosine squared x. So that's just 1 over secant x. I think this is why I tried to do that before on that last problem. Switch this, or cosine, sorry. Because on this one I can switch 1 over cosine x to 1 secant x. So the answer to all this is just secant x. So, all right, so there's an example of using chain rule. So you're going to have to use chain rule or product rule on these ones, but your derivatives are on 466, but the integrals are not. Then there's no integrals. So what you're going to do is you're going to have to go backwards. So when you have an integral problem, you have to look at what you're taking the integral of and see where does this, which is like this, look on the page at 466 and see which one of your derivative answers is this. What derivative you're taking that gets you this answer, and that is inverse hyperbolic sine. So then you can go ahead and you might have some matches up just like that, but most likely you're going to have to do substitution rule, right? So chain rule for the derivatives, substitution rule for the integrals. Okay, this one is straight, right? It's like this. So that means I can just look, this is going to be hyperbolic sine. So the answer to this is just hyperbolic sine, inverse hyperbolic sine from 0 to 1. Now I look up what is the definition of that. And the definition of that is the ln of x plus square root of x squared plus 1, yeah. Now I can plug in my 1 and plug in my 0, my a, and plug in my b. And 0. And you can start simplifying this. So this would be just 1 plus square root of 2 minus ln of 0, 1, 1, square root of 1 is 1. And this is just 0. A lot of these, remember when you subtract 2 logs with the same base, then you can put that under 1 log and you're just dividing those. 1, that's just 1 then, so it's just ln of 1 plus root 2. So there'd be your answer to those. So those are the definite integrals, but realistically you're going to do a lot of substitution rules. And if it's not a definite integral and an indefinite one, remember you just add c at the end and you won't have to do all this part. So that's only for definite integrals. All right, so the next video I'll do more examples.